design problem or a scaling problem. Okay, so أول شغلة بدي أقولها هو give me in the chat proposals for a certain product to build, or a certain system that we would like to design. And then based on the feedback, we're going to pick one and we're going to design it together. And I'm going to show you how you can build it from small, and then we can scale it up to, start serving hundreds and millions of users. So would you like to start dropping stuff in the chat, please? Any thoughts? Thoughts could be like, let's build Instagram. Let's build Facebook. How can we build YouTube? How can we build GitHub? How can we build, I don't know, anything that you might come up with, anything that you are probably curious about. So can you please do me this favor and drop stuff in the chat? And if I don't see anything in the next 5 minutes, I'm going to leave. Can you hear me well? All right. GitHub, YouTube, nice. All right. Be a little bit more creative. Anything? Facebook, Uber. Yeah, interesting. Uber is an interesting problem for sure. Anything else? Blockchain, crypto, streaming service like Netflix. Amazing. App that connects people based on their movie taste. Okay, interesting. Yeah, I see some awesome contributions. Yalla, keep them coming. I want to hear more. Give me more ideas, and then we're going to pick something together and we're going to design it. Wow, this is to show you that I have not prepared this Tinder. Yes, sure, Sharbet. I have not prepared this, so we're going to do an impromptu software design session together. If you do any interview in big tech, this is probably some of the stuff that you're going to be seeing. This is stuff that you're going to be quizzed on. This stuff you need to pick up, you need to learn as you grow in the market. It's not enough to know, your object-oriented programming information, or to learn the syntax of some programming languages. This is the meat of what we do in terms of software design and software architecture. Yalla, I need more ideas, please. Give me maybe 5 more, and then we'll pick from the list something. OpenSea, very nice. What else? Dating app, Tinder, yes. Yalla, maybe someone might drop their final project. Can you share your YouTube channel name? Yes, I'm gonna drop the link now. You can go to this URL, and this will redirect you to get to YouTube. Thank you, Kareem. Yes, yalla, more ideas, please. Give me a couple of more ideas, and then we'll get started. Airbnb. Okay, sounds good. Twitch. All right, awesome. Streaming video. Okay, so let's Internet of Things. All right, sounds good. Internet of Things is an interesting problem because we have a lot of different clients. Let me share my screen where the iPad is, and then we can get going. Let me try to share this. All right. So this is my iPad. This is where I'm drawing stuff. I hope you can see it clearly. Please let me know if you have problems seeing my my display.
It's clear.
Perfect. Thank you. All right. This is where we're going to be designing stuff, and we're going to be talking about what we're going to do. So let's pick something. YouTube, I'm not going to go into the streaming video stuff. We can, but it might involve some topics that might be difficult to explain or process. Can we pick something with security? We're going to talk about security no matter what we're going to describe, Muhammad, so don't worry. Let's maybe pick something like, I don't know, Facebook, Uber, GitHub. All of these are good options. Tinder, OpenSea, كلهم هول, they're going to look the same, to be honest. لأنه كل هول, they are sort of web with mobile clients, so they're going to follow the same principles. So let's start with, I don't know, maybe Facebook or Uber. They're going to follow the same principles, so don't worry, it doesn't really matter. Let's start by discussing a little bit how we can approach something like this. You are currently used to the 3-tier type of architecture, and what the 3-tier type of architecture means is we have a client, whatever that client might be. It can be our browser, right? It can communicate via the internet to some server where we have our web server installed, right? This could be a machine, whatever that machine is. And on this web server, we're probably going to have something like Apache. I'm not sure what web server you are using currently, but let's say Apache. You could also have other options like Nginx or يمكن Tomcat. It really depends on the technology stack, right? On this web server, you also have MySQL, which is your database. And I think this is what the basic setup that you currently have, right? On this level, you're going to expose port 80, and through port 80, you're going to basically handle all the HTTP traffic. If I'm saying nonsense, please also ask your questions directly in the chat. I'm going to keep an eye over it there, and I'm going to answer them right away. So what do I mean by client? Your client could be your, I don't know, laptop, right? It could be a laptop. It could be your mobile phone. أنا أيامي the mobile phones had an antenna, and maybe I don't know, maybe your fridge could be like one of the clients, right? We know this already. Probably we've discussed this stuff with Sharbir already. And these clients, all of them can make HTTP requests through the internet, right, all the way to your port 80. And for these requests then to be handled by the web server. And on the web server, of course, you're going to have probably an interpreter for your language. You're using PHP, I'm assuming. So using PHP and Apache, we're going to basically return a response back to our clients, and then they're going to display something on the UI, right? This is, in general, how it works. If we're going to build Facebook, when Facebook started, it looked exactly like this, right? There was nothing really major going on. It was a very simple web server, programming language, database type of setup. Nothing really fancy was going on. Probably in addition to the port 80, they had port 443. Why? Because we wanted to serve HTTPS traffic. And with HTTPS, obviously, we needed to install the certificate over here, the TLS certificate, for us to be able to do SSL traffic. What SSL traffic means is whenever we create a request, HTTP request coming from the client, before this, when this request is made, we need to start a process called SSL or TLS handshaking. And what this means is there is going to be an exchange back and forth of keys. We're not going to go into the details of this protocol. All you got to do here is, all you got to know here is that SSL allows us to verify the authenticity of who we are talking to. It allows us to really know that we are talking to Facebook, because there is some third-party company or entity, whatever that entity is, that has verified the certificate here, and it said that this is indeed Facebook. And by doing this handshaking thing here, we know that we are talking to the proper system. Now, this setup right here, you will be surprised by what I'm going to say right now. But with this basic setup, you can serve hundreds of thousands of users. Yeah. A lot of companies, a lot of startups, when they begin, they start building these very fancy, gigantic architectures, expecting إنه نحن we're gonna grow to millions of users like overnight. فلازم نعمل something extremely complicated ونقعد نعمل over engineering for a lot of stuff. It is not necessary at all. This is the basic setup. This 3-tier architecture can take you to hundreds of thousands of users. When we start talking about hundreds of thousands of users, then we can start talking about the more complicated problems. وهلا رح نبلش نفوت بهول complicated problems and see how we can scale this. So keep this in mind when you join your companies after you graduate from SE Factory. Do not over-engineer. This is lesson number 1. This basic stuff can serve you and take you a long way. How? By doing something called vertical scaling. And in any system design interview later on in your careers, you're going to talk a lot about horizontal versus vertical scaling. Vertical scaling means that we have this, we have this machine over here, which we call the web server. This machine, let's say we started with 2 CPUs, right? It's like a VM in the cloud, or whether it's on-premise, bare metal, whatever. Right? أعطيناها 2 CPUs وأعطيناها 8 gigabytes of RAM. This was our starting point, and our disks, maybe we gave it 100 gigabyte. It's very small. This will probably help us serve maybe 1,000 concurrent users at the same time, probably not more. And then we keep increasing these values over here. We can go up to, I've seen servers go up to 128 virtual CPUs. I've managed servers of this scale. You can have maybe 2 terabyte of RAM. Yes, don't be surprised by these numbers. This is feasible. And maybe you can have 1 or 2 petabyte disks. That's also feasible. So imagine بعد ما حكينا ب any other component عندنا بس هيدي ال VM الوحدة اللي هي حاطين عليها web server, PHP and MySQL all in the same place, right? We can scale it up in terms of size and vertical scaling up to 128 CPUs, 2 terabytes of RAM, 1 petabyte of disk. Of course, this is expensive. Things will start breaking down at this point, but I'm just giving you an idea of how far you can go with the size of one machine, right? This is one VM. I think you took an AWS course. I think you understand now some cloud principles. So let us move from this basic architecture to host more complicated stuff and start adding things to it, right? We are building Facebook. So I'm gonna slide down over here. We're gonna introduce a few things that will help us scale. And please, if you have any questions so far, drop them in the chat. I will answer them right away. Over here, we're gonna keep the client layer. So, and this time we're gonna limit the clients to mobile apps, right? Because, or web browsers. So we have our laptops over here where you can access Facebook via your web browser. And we have our mobile phones over here where you can access Facebook on the mobile phone. And it's funny that Facebook started with the browser application, but they didn't want to jump to mobile. And now they are mobile first. This will tell you something also about trends, right? From the client side, ما راح يتغير شيء كمان. These two clients will basically make HTTPS requests, right? Because we want our platform to be secure. Through the internet, we're gonna make the internet a cloud over here. We're not gonna change much. And هلا بدنا نغير on the AWS side. Let's say we are using AWS to host our platform. How can we make it a little bit more scale friendly? First of all, one machine is not enough anymore. We need more. وهون بنبلش نحكي in the realm of horizontal scaling. Horizontal scaling as opposed to vertical scaling is vertical scaling, you add more resources to one machine. Horizontal scaling is adding more machines. So adding more of the same. But you ask me, how can you deal with the HTTP requests going to multiple machines? Don't we need to have one machine that can handle the traffic? How do we approach a problem like this? And the great question, the answer to that is to introduce an appliance called a load balancer. Sorry for my horrible handwriting, but let's assume that هذا اللي كتبته هلا it's a load balancer, right? The load balancer will sit right behind your internet layer, your internet, whatever that internet is. Of course, the internet is nothing but routers, right? So the routing the traffic, moving the traffic from one route to another. The first thing that's going to receive our HTTP request is going to be the load balancer. But how is this load balancer configured? The load balancer will have an IP address. Of course, if you study DNS, if you know how traffic routing works, you understand that every publicly exposed machine, every machine exposed to the internet has to have, are we supposed to be seeing what I'm writing? Yes, you're supposed to. I'm not sure.
Yes, Bassem, I can see.
Yeah. Awesome. Thank you for the confirmations. Karim, you might want to double check your internet. I can zoom in a little bit and make my handwriting clearer. But no promises because I'm a horrible handwriter. So let's call this LB, short for load balancer. And as I mentioned, any machine that is connected to the internet or any network needs to have an IP address. So let's say the IP address for this load balancer is 10.0.0.1. Of course, publicly exposed IP addresses do not belong to this CIDR range, but let's assume for the sake of the example that it has this IP. Obviously, we're not going to ask people to connect through an IP address. We're going to add something on top of it, which is called DNS. So how do we deal with DNS on the AWS layer side? They have a service. It's called Route 52. And Route 52 is a service provided by AWS that allows you to register domain names, DNS, and map these domain names to IP addresses, right? So we can say on the Route 52 level, I want to connect this domain name, which is like facebook.com, to this IP address. So anyone connecting to facebook.com will resolve this IP address over here, and then the traffic will be routed to the load balancer. So when the HTTP request that starts over here, right, goes through the internet, before it hits the internet, on the machine itself, there is something called a DNS resolver. It's probably in your router. It could be in your browser. There are multiple layers of DNS resolvers. DNS resolver is gonna query Route 52, and it's gonna ask for facebook.com, what is the IP address, right? And then Route 52 will return the IP address to the DNS resolver, and the DNS is going to know the IP address. So when the HTTP request goes out, it doesn't go to a DNS, it goes to an IP address, and then the request will land on the load balancer level. Of course, here, you're going to ask me, okay, what happens to the TLS or SSL handshaking? This is a problem called TLS termination. Okay, we're not going to really dig into the details over here. Just know that you can do the termination either on the load balancer level, or you can do it a step further, which I'm going to show you in a little bit, but just keep that in the back of your head. Now, what is behind the load balancer? Behind the load balancer, we're going to have a few extra stuff. And I'm going to add a few extra things also in parallel to the load balancer. One of them is I want to add a firewall. Why do I need a firewall? Because it's Facebook now, right? There might be some agents who want to bring Facebook down. Why? Because they have their own network that they want to promote, and they want to show that Facebook is not a very good product. So how can we protect against these things? We can protect by setting up a firewall. And what firewall will do is it will allow us to move the traffic that instead of it going to the load balancer directly, the traffic will instead go through the firewall, and then from the firewall, we can jump back to the load balancer. And the firewall will make sure that if anyone is trying to hit a port that is not port 80 or port 443, right? If they're trying to hit, let's say, port 52 or 53, whatever, this request will be denied. So the firewall will be able to protect us. The firewall can also protect us from common security vulnerabilities. We can have something called like a web application firewall. It can protect us from SQL injections. I'm not sure if you did a session on security, but let's just say that there are currently appliances that you can put in your environment that protect against these things. It can also protect you from DDoS or denial of service attacks. So if someone has a lot of bandwidth, okay, thanks, Shadbil. Just so you know, security is very, very important. SQL injections, DDoS stuff, you need to be aware of them. Even if SE Factory does not cover them yet, you need to know because you are responsible for the security of your application at the end of the day. So again, the firewall will protect against these things. The traffic now moved from the firewall to the load balancer. On the load balancer level, we will have an algorithm. We will have some logic. The logic is going to decide where is this request going to go to. So behind the load balancer, we're going to have the first web server. We're going to call it Web 1. And then we're going to have another web server. And when I say web server, I mean simply a virtual machine that we are going to call Web 2. And these are, if you've taken AWS, these could be simple EC2 machines. Nothing really fancy. Is the firewall software or hardware? You can decide. It could be both. So on AWS, you can buy a software level firewall. or you can have a dedicated appliance, a dedicated, what do you call it? A hardware firewall that is for you. Of course, the price is going to change. So the load balancer also can be physical, and it can also be a virtual load balancer. Okay, so you can decide. It depends on how much you want to pay. So load balancer over here will split the traffic based on some logic. I'm gonna draw a brain. This is a brain. Don't ask me how, but let's say this is a brain. It's gonna decide whether to push traffic over here or push traffic over here, and this brain is gonna be responsible to make sure that the response also goes back to the same client. So you need to understand is that when we start a request over here, and we go through the internet, then through the firewall, and then through the load balancer needs to make sure that the session is persisted. So if the traffic goes to web 1, the response needs to come from web 1, and the load balancer needs to send it back to the client that requested it. And if it also, and then the future requests, if we are the future requests can be the same request has to be returned to the same client. We cannot have a request made for web 1 and then web 2 responds with the response. That doesn't work that way. Okay, that's also why we call REST APIs or REST or HTTP in general stateless, because you don't necessarily have to always route the traffic to just the same device. So for example, if I have one laptop over here connected to facebook.com, which is me, my Facebook, I don't always talk to web 1. I could be talking to web 1 for the first half an hour. Maybe web 1 gets very busy, the traffic gets split to web 2. That's totally fine. But as long as the single HTTP request cannot be split across multiple servers, right? But subsequent or sequential HTTP requests can be distributed to different servers. Now, this is the compute layer. This is, we're going to call it compute layer. This is a term that you're going to hear a lot, right? A term you're going to hear a lot is called compute. It can come in different forms, EC2 in this case, but later on, you're going to start hearing about stuff like Kubernetes. You're going to start hearing about containers. You're going to start hearing about so many different things. Let's stick with the basics for now, and I'm going to show you how you can scale to Kubernetes and deploy much more advanced stuff. So load balancer will route the traffic to either web 1 or web 2. On web 1, we're going to have our PHP interpreter, right? Just as usual. And instead of storing everything on the root disk of our EC2 instance, we're going to this time attach new new EBS blocks, elastic block storage, right? We're going to attach new disks to both of these appliances. Now you will ask me, Bassem, what will these disks contain? Well, they're going to contain basically a copy of your web app. They're going to contain all the data of the customers, like session files, right? They're going to contain maybe not necessarily images. They could contain images, but I'm going to show you a little bit how you can deal with, in a better scenario, with images and static assets. I'm going to show you that right away. But let's just say that EBS is going to the EBS block or disk is going to contain a lot of the different assets, maybe the code of our web application. And whenever we deploy, this is going to be a big thing. Now we're not just deploying to one web server, we're actually deploying to 2. And you need to keep that in mind in your deployment process, that now we are dealing with horizontal scaling. We need to, deploy changes to 2 web servers, and we need to take care of 2 web servers. So complexity increases. Now 2 is easy still. Let's think about how can we deploy 2000s. We're going to get to that in a little bit. So, and then from the web servers, we're going to have our database layer. And on the database layer, there are multiple configurations that will allow us to scale. The simplest configuration is where we have just one database. We're going to call this DB1. And this single database is basically where we keep all of our information. It could be MySQL, PostgreSQL, whatever database you prefer. We're not talking about anything NoSQL yet, because even Facebook and GitHub and whatever other company you can think about, they all need SQL relational databases. There is a trend going on that NoSQL is the big thing. MongoDB, Redis, all of these fancy names. All of these databases are fine. I'm going to show you now how to use them properly. But at the building block of all of your apps have to be using relational databases. You cannot escape them, okay? Now, how do we deal with what is something wrong with this picture? What's wrong is we're going to have web server 1 and web server 2 communicate with the same database. And we're going to have web server 1 read and write to the same database, right? Because we are maybe querying. How do you read and write? You query the database, right? You either do an insert or you read by doing a select or whatever. So we are reading and writing to this single database. Okay, I'm going to ask you a question. What happens if this database goes down? We're going to have a big problem in our hands, right? If the database goes down, bye-bye. Facebook is out. So how do we deal with problems like this? We have two options over here. The first option, and it really depends on the database you are using, but the first option is to have a replication, right? Replication means any transaction that you write on one database gets copied to the second database. So this picture is wrong now. What this means is this database 1, and this is going to be DB2. This is going to be our write database. And this is going to be our read database. What this means is we can only write to this database. And then through replication, through the process of replication, the data is going to be copied to DB2. And we can only read from database 2. What this means is we need to configure our web application to write the queries on database 1, and even web 2 will basically write to this database. This will spare us the headache of thinking, how can we maintain the consistency? We don't need to worry about that because the database is ACID compliant, which means that it's responsible for maintaining its own consistency. We're not splitting the data. We're not dealing with distributed systems problems here. You know, we're just writing to one location, and that's fine. A database can handle multiple clients writing to it. That's okay. Okay? But the replication will make sure that both of these databases are in sync. And then when we want to read, right, we can use this database to read information. So whenever you want to do an insert, you do it on DB1. Whenever you want to do a select, you do it on the DB2. This is one approach. Now you ask me what happens if database 1 goes down. You basically simply need to have some failover mechanism. And the failover mechanism basically tells web server 1 and web server 2 that you need to promote this database to become the primary. And then this database will be responsible for the write and read operations. Okay. And then web server 1 and web server 2 will connect to database 2. This is in the case of database number 1 goes down. You might say, okay, but this is really complicated. Like, what happens? Yes, it's complicated problems. And this is what happens in the background. So whenever GitHub goes down or whenever Facebook goes down, it's probably something like this that has already happened. And the failover systems have kicked in. And there's going to be a lot of headaches. There will be people on call scrambling to solve these problems. And, you know, these are very complicated issues. So when we talk about horizontal scaling, this is really, really annoying stuff that is very difficult to resolve. Now, how do they solve it? Yeah, I can explain a little bit on that. It's a nice thing to follow. So we call this ops. We call this site reliability engineering. We call this operational work. There are teams. The development teams are we have two separate teams. So we have the platform teams. The platform teams are responsible for designing what I just showed you right here, right? And then the development teams are responsible for building the pipelines that deploy to these environments. They build the code, they build the application, they make sure that all of this logic is properly working together. But the site reliability engineering teams are the ones responsible for checking the database health, making sure that the database are up and running, making sure that if there's a crisis, that it gets resolved. Now, how does that happen? Let's say database 1 goes down. We have tooling that monitors the database all the time. And if the database starts spiking in certain areas where we have a lot of concurrent writes, or the database is not able to handle all of this traffic, we get warnings, we get paged, we have pagers, we get notifications, and there are people who are on call, even developers like myself. We are always on call. We are responsible for the infrastructure that we own and the services that we own. We get paged, and then we have to jump, and then we start investigation. The first action that we have to do is we have to get the site back up as soon as possible. The concern is not to really fix all the problems right away. The concern is to go back in business. That's the main important thing. And try to avoid data loss as much as possible. Once we get to the state where we are back in business in whichever way, shape, or form, it could be like doing the failover I just described. The next step would be to do to take some rest, of course, and then the next step would be to do a root cause analysis. And the root cause analysis is just a gigantic investigation. We start digging into the logs. We start looking into what happened prior to the incident. We build a timeline, what happened exactly at each step in time. Where did things fail? We start trying to compile a picture, like an investigation, like any, I don't know, detective story. You just start looking for clues, and then you compile the timeline. And then once we do the root cause analysis and we are confident that this was the actual problem, we fix it. And then we document it so that in the future, if it happens, the team will have a playbook. They will have a guide for how to resolve similar problems down the line. So can you restore the database 1? Restoring is an option, but we don't do these types of things as the first response. It's very dangerous for you to come and restore a database. We don't do that. First, we do a failover. It's very important. If you want to do a restore, it's a very time-consuming process. You need to guarantee consistency of the backup and the backup after it gets restored and all of that stuff. That's not something we do right away when something goes down. First, we do the failover. So DB2 will be the primary now, and it will be the one responsible for serving the traffic or the requests. And then once we are confident that DB2 is working as it's supposed to, and we identify the root cause, then we fix the root cause. It might not be a restoration. The root cause might be that the database needed more resources. So we scale up, we add more resources to the database, right? Restoring a database is not always the fix to everything. Is it the norm to have 2 databases? 2 databases is nothing in our world. So when we talk about databases, we talk about clusters of hundreds of databases. And 2 here is just a simple example, because if I'm going to talk about hundreds of databases, then it will take us a week just to describe the architecture, right? But yes, it's the norm to have at least 2 databases. Okay. Now, I want to talk about a few things that can also help solve scale problems. This setup that you see right here can help you probably scale to, it really depends on your application. But in the case of Facebook, we're talking about images. We're talking, about, people signing in and out. Yeah, it can probably help you scale to tens of thousands of users, maybe hundreds of thousands. Probably tens of thousands concurrent users, not more, because the load balancer will start to complain. Do you duplicate the whole structure when making a staging environment? We do not have a staging environment per se. It depends on the company. But if we're talking about something like Facebook, we don't have staging environments. We don't believe in staging environments, or GitHub. What we do is we have testing environments that are sort of similar to this, but on a smaller scale, that each pull request maybe if we talk about continuous integration, continuous deployment, this would have been the topic. But basically, you don't replicate everything. No, you have a smaller set, and then you deploy and test in that small set. Maybe you test with production data. Sure, that's fine. But yeah, these are smaller environments that you create on demand. But basically, what we do is we deploy to production immediately, and we deploy to production using a strategy called the Canary deployment or Canary releases, where we deploy to a small percentage of users, and then if we start seeing problems, we roll back, and then if we don't see problems, we increase the release to 20%, 50%, and then make it available for everyone. And while we do this release process, we are monitoring the health of all of the services and make sure that there are no spikes, no errors, so on and so forth. But again, I don't want to talk about releases yet because that's a whole tech talk all by itself. We're just going to talk about scaling at the moment, and we'll probably touch upon some good practices when it comes to CI/CD. You mentioned trying not to lose as much data as possible. Yes, but aren't we replicating the data? I don't know if you talked about it, but I got disconnected. Yeah, sure. Great question. We are replicating the data. That's true. But the replication does not happen in real time. The replication, there's a small delay, right? So when we talk about like 1 transaction per second, that's not a lot. That's fine. The replication will handle that. But when we're talking about 1,000 writes per second on the database, the replication will definitely not have a throughput of 1,000 writes per second. It's probably going to do 500, 600 per second. And then the remaining 300 will be batched in the next second, right? So if my database goes down at a certain point, I might have a certain backlog of transactions of maybe 300 transactions that did not go through, right? So what do you do in this case? This is the problem that you need to solve. Again, distributed systems are very, very difficult. RPO, RTO, again, these are old principles, but yes, they kind of, we don't talk about RPO and RTO in our world. We talk about service reliability. We talk about service uptime. We talk about SLAs. We talk about service level agreements. Yes, RPO, RTO, they recovery time, and the data loss time. Acceptable data loss quantity. They're good principles to follow, but they are part of the old model, the DTAP, development, testing, staging, production environment. We're talking about highly scalable, high traffic environments like Facebook, GitHub, where we do continuous deployment all the time. This split of environments does not make sense anymore, and this reliability, the RPO, RTO, does not make sense also anymore. So we need to guarantee that this data is never lost, right? So imagine if people are pushing very sensitive stuff, and then we tell them, yeah, sorry, we lost your data, that's not going to play well. There are a lot of mechanisms to play around this. But again, let's stay on topic a little bit. I'm going to show you a little bit of more interesting things. But these are great questions to ask, and thank you for asking them. We're not done yet, right? There is still one topic I want to cover, which is in this small setup over here. Yes, it's small still. We static images. Where do we put them? JavaScript files. Where do we put them? How do we deal with this type of stuff? You might tell me, okay, Bassem, why do we have the EBS block in that case? Can't we put them on the EBS block? Sure, that's one way, but the EBS block means that you're putting pressure on your web server to serve this content. Why? If you can put it somewhere else. Where would that other place be? That place is called blob storage. And if we are talking about blob storage in the context of AWS, we are talking about S3 buckets. Yes, it's a bucket. Blob stores are not like EBS blocks. They're not file system storage. They do not have disks that behind. Well, they do have disks, but we could have an array of disks. It doesn't have to be connected to an operating system like EBS blocks do. You don't have to mount it anywhere. S3 buckets, they provide you with an API. And using this API from the web server, you can connect, you can store, you can store using the API information on the bucket. This information could be PNGs, images. It could be your JavaScript files. JS. It could be, I don't know, some other static content. It could be videos even. So for example, when you make a request to YouTube and you say, I want to play this video, the video does not come from the disk on connected to the web servers. The videos will come from the S3 buckets. And what the S3 buckets can provide you with is a unique URL, right? It's a unique URL per asset. So you can get a URL for each image, for each item of these. So you can get a unique URL for any of these items, right? And you can connect and you can make this URL session bound. So it could be specific to a certain session. And then when the response goes back, sorry, it's getting messy, but when the response goes back to the client, you send back also the URL that comes from the S3 bucket, so that when the browser wants to load the image of a certain person or maybe a video, they basically load it from the S3 bucket URL over here. Okay. Then from S3 buckets, we can talk about another layer of dealing with static assets, which is called CDNs. Yes, Muhammad, I will take your question. Give me 1 second, please. We're going to talk about content distribution networks. And the content distribution networks, they have as a backend the S3 storage. But what content distribution networks do is that they can allow you to distribute the content of the bucket to different locations around the globe. So location 1, location 2, and then location 3. And what these locations could be, let's say this one is US, this one is EU, and this one is Asia. And then instead of getting the URL from here and serving all the content from the US, then the content distribution network will make a decision like the load balancer, but it will make a decision over here based on the region where the request is coming from. So if the request is coming from Lebanon, the traffic will be redirected to Asia, for example, maybe even Europe. It really depends. And the content distribution network will make sure that all of these locations, so when you upload something to the S3 bucket over here, the content distribution network will make sure that it's replicated to all of the locations, so that whoever on the globe asks for this content, wherever they are able to receive the URLs for it and display it on the client side. So, Hamad, you had a question.
Yes, I have two questions actually. You said the S3 bucket will directly send the URL to our computer, to the client, without passing through the server.
No, it will pass through the server.
Okay, it will pass through the server before sending it.
Yeah.
One more question. Why do we need the EBS if we're using the S3 buckets?
Hello. Great question. So the EBS is going to store your code files, your code. It's going to store the logs, maybe temporarily. It's going to store everything that you need to serve requests. Maybe it will store credentials. It's not a good idea, but it could be. Okay, so you still need the EBS block to function. But when it comes to images, JavaScript files, videos, this type of content, you don't need it to serve a request. This is not the logic, the business logic, right? This is just extra material.
Okay, so the EBS stores like our code, and the S3 stores the data.
Well, I mean, both of them are data. Even the code is data. But you can think of the S3 like storing images, JavaScript files, videos, CSS, anything that is not necessary for PHP to render a page. Any asset. Yes, thanks, Bilal.
Okay.
Like in Laravel, don't you have a folder for assets or something like that? You should. So this folder, for example, can go into S3. And then the content distribution network will spread it out across different geographies. How are we doing so far? You're still following up with me? Shall we continue? We can scale this. We're not even, we haven't even scratched the surface of how far we can go. Can I get some confirmation in the chat? All right, all good, great. What can we do next? A lot of stuff. Let's talk about it. So how can we introduce NoSQL databases to this? Like, how can we add Redis? How can we add MongoDB? How do we deal with all of this stuff? How can we build an API layer that maybe the developers, you know, who build applications on top of Facebook could use? How do we do all of that stuff? Great. Let's start again with the clients. Right, and this time we're going to have a laptop over here, which is going to have a browser, but also we're going to have a developer laptop this time. And we're going to call this one dev A. And this developer laptop is going to be basically calling APIs and all of that stuff. They're going to be building apps on top of Facebook. They're going to be doing authentication, OAuth, and all of that nice fancy stuff. So how can we deal with these people? And then on the same client side, we also have all the teenagers nowadays, right? The teenagers, they're always not on Facebook, probably on TikTok, but let's just say they are high traffic consumers, right? They just want, they're on their phones all day long, and they are chatting, they are doing all sorts of stuff. So they constitute high traffic customers. How do we deal with them, and how do we scale to serve all of these angry mob of teenagers? Let's recollect a little bit here. So we're gonna skip a few steps because we don't have a lot of space. So we're gonna make the internet smaller than it is, right? And then all of this traffic is gonna go through here, HTTP requests, and all of this goes through the internet. Now on this side, we're gonna have let's see, we had the load balancer, we had the firewall. Let's replicate those. So firewall, I'm gonna call it FW for firewall, and then we're gonna have a web application firewall, and then we're gonna have, instead of a DNS, we're gonna have something called GeoDNS. And then instead of one load balancer, we're gonna have multiple load balancers now. So we're gonna have load balancer 1, we're gonna have load balancer 2, and then we're gonna have different regions. So this is gonna be Asia, this is gonna be Europe, because now we are global, right? Facebook is scaling and we are serving multiple continents and we have a lot of traffic. So GeoDNS, instead of it connecting to one load balancer, GeoDNS allows us to connect to multiple load balancers in different regions. And the firewall and the web application firewall, they're not region specific, so they can be in front of everything. And then the traffic goes through this, and then, you know, it basically goes to the specific region based on the decision that is made by the GeoDNS. And then from the load balancer, we're gonna have a scale set. It's called in AWS, sorry, shouldn't have deleted this. In AWS, we call these autoscale. And what the autoscaler does is it creates new EC2 machines. So instead of having web 1 and 2, we're going to have web 1, web 2, 3 dots, and then web n, because the n could be any number. And then the autoscaler will make sure that these are properly connected to the load balancer, and the load balancer will still determine where the request is going to go to which server. So basically the autoscaler will make decisions to horizontally scale and add more machines as we have more traffic coming in. And the autoscaler will allow us to really meet the demand of these pesky teenagers that are hammering our infrastructure. Now, in addition to this, we're going to have a caching layer. So we're going to have a cache over here, and on the caching layer, we're going to have a bunch of stuff. So one cache, we're going to have something called memcache. Maybe even we're going to have some Redis instances, right? And then we're gonna deploy a different software architecture. So instead of doing a monolith is basically where we use one Laravel framework. We have all of the application in it. We're gonna start distributing our application into microservices. And this is where, you know, the beauty of microservices comes in. Probably this could be the step after this one. I think we still have 30 minutes, so I want to cover the caching layer first, and then maybe we talk about microservices. Of course, in Europe, everything that I've drew in this zone, it's going to be replicated over here, right? So think of Europe as exactly a clone or a copy of everything over here. Now, behind the caching layer, we're going to have our database setup. And now we're going to have a something over here, which basically deals with clusters, maybe something like Vitesse. And then we're going to have here not just one database with replication. We're going to have a cluster of databases, which could be 1, 2, or n number of databases, right? And the tool that we added over here will basically deal with the read-write consistency and all of that problems. Muhammad, caching layer, I'm going to describe in a bit. So this is the memcache or Redis. What are those and how do we use them? Fantastic. You remember from the previous conversation that when the request comes to the load balancer, it goes through the web server. The web server is going to pick up some stuff from the EBS blocks, right? We're going to have here a farm of EBS blocks attached to these VMs. Each one of them will have its own block. And then once we want to render the page, we might even need to pull data from the database. Now, instead of going directly to the database, we go to the caching layer. And the caching layer is nice because the first time you make a request to the caching layer, and the request could be select top 10 from the table customers, I don't know, or select the user that has the ID 100, or select the user that has the ID that starts with Bassem. I don't know what's your query, whatever it is. Instead of going directly to the database, we hit the cache first. So we ask the cache, do you have the results of this query? If the cache says, no, I don't have it, the cache will be responsible for going to the database, fetching the information from the database, storing it in the cache, and then returning the response to the web server. Why is this important? Because the databases, they will write the data on disks. They will write them on EBS blocks or something similar to EBS. And writing on the disk is expensive in terms of time cost. Writing on a disk is an operation that takes time, even if it's like 20 microseconds or milliseconds. 20 milliseconds is a lot. When we're talking about stuff like Facebook, we're talking about rendering the entire page, right, in less than a second, which means that a request of reading something from the disk of 20 milliseconds is a lot. We cannot afford this. We want a response in maybe 1 or 2 millisecond stops. So how do we get that response? We get it from the caching layer. Why? Because the cache over here, for example, memcache or Redis, they do not store the data on disk. They actually store it in the random access memory. They store it in RAM. And then you can give memcache, for example, let's say 128 gigabytes of RAM for each copy of the cache, right? And RAM is instantaneous. It's very, very fast. You can get like a response from memcache in like 1 millisecond. If the data is gigantic and we're talking about hundreds of megabytes, of course, it's going to take more time. But if we're talking about like, I don't know, a few bytes or a few kilobytes, that's nothing. That goes really quick. So the web server will fetch this information from the caching layer right away instead of going to the database. And the caching layer will be responsible for making sure that its data is always up to date. Now, you ask me, Tab, but 128 gigabyte is nothing. That's nothing. The database could be like terabytes in size. Yes, great. The cache is hot. In terms of, sorry, the way the cache works is it will only cache and store whatever the web servers demand. If there is information that is not accessed all the time, there's really no point in caching it. Why would we cache it? Because if no one's asking for it, right? So the way the cache works is when it makes the request to the database and stores the information, I'm gonna make this X, for example, is the information we stored on the cache. It gives it a time to live, a TTL, and this TTL could be 5 hours. And if in 5 hours nobody used this this hit or this item, it will be evicted. It will be cleared from the cache. So the caching layer will delete this from its memory, and it will reclaim the memory. So that's why we can have, like with a 128 gigabyte, serve a lot of content and a lot of traffic, because it's not persistently storing everything in the database. It's just storing the information that is very, very highly in demand right now. Right? That's why also this is not all automatic. There are teams, site reliability engineers, that are responsible for doing what we call a hot loading or hot reloading of the cache. They basically prime the cache with information that we think that the people will want at a certain point in time, right? We get it from the database, and we make sure that the cache has relevant information to serve. That's why when you load Facebook, no matter where you are in the world, right, you get responses instantaneously. Even if they're serving the request from the United States, the traffic latency or the delay in the geographic delay, right, is minimal, because we got a lot of speed from the cache, for example. And then the next speed advantage we get is from, again, as I mentioned, the non-geographical bound block storage. So I'm gonna just make Europe a little bit smaller because I need the space over here. So let's just say that Europe is basically a copy of this, right? And then here I'm gonna put the non-geographical assets. So we have S3 buckets that have a lot of information, right? And you have the CDN that is basically copying our S3 bucket to different regions across the globe. R1, R2, R3, right? And then the S3 bucket assets go back to the web servers, and they are returned as URLs through the HTTP request that came in. Let's color those in red, just for you to get clarity on the response. Any questions so far? So we introduced caching in this layer over here, and showed you how you can speed up your database responses. Yes, Muhammad.
Yes, a small question. Does GitHub use a caching layer?
Of course.
That's why when we push a code to GitHub and try to check our website, the index.html, the web page, it doesn't
yes,
update directly.
Yeah, it takes a little bit of time, because we want to avoid hitting the database as much as we can. The delay that you see is basically the cache being primed. It's basically the cache going to the database, asking for the data, putting it in the cache, and then serving it from the cache. The next time you hit it, it would be super fast. So we have here concepts of real-time and eventual consistency. So real-time, right, consistency, and then eventual consistency. And these are principles in distributed systems, that you need to be aware of. That are very important. Eventual consistency means that eventually, after a certain period of time, and the goal is to make that period of time as small as possible, the system overall, like everything you're seeing on the screen right now, will be consistent in the sense that it will have the data from everyone. It will be able to serve the data from everyone, and it will, everything is stored on the disk. Everything is safe. We have backups that are running in place. We have replication maybe to another region, right? So we have a cluster in region 1. Maybe you are replicating it to region 2, the data, so that if region 1 goes down, and it happens, a data center can burn. Keep that in mind. Physical catastrophic events can happen. An earthquake can happen. A tsunami can happen. So when we design at scale, we need to think about all of these different problems, right? All of these are important things to consider, because when you're building something like, I don't know, a small app serving Lebanon, that's okay. You can have 2 locations, and that should be fine. Maybe even this can serve half of Lebanon, if not the entirety of Lebanon. But when we start talking about maybe the Gulf, for example, then we need to start looking at something like this. When we start talking about serving the entire world, we need to start talking about architectures that probably look like this. And I can add more stuff to this to make it even more performant. But again, we don't want to over-engineer, right? So we address problems as they arise. Whenever I start seeing a problem, certain types of customers that come in, they're not really getting the responses very quickly. Then we start addressing and adding layers to solve problems. In addition to all of this, we need to understand beyond real-time and eventual consistency is how do we guarantee the site reliability? We guarantee that with monitoring. A lot of the information that goes through the system, it is compiled in monitoring solutions. And these monitoring solutions, they give us dashboards showing us traffic spikes. They give us dashboards. How many 500 errors are we seeing? How many 200 responses, HTTP responses, are we generating? We monitor the traffic. We monitor the delay. We monitor every single piece, nook and cranny of this entire system to make sure that we have something that is working really well. And whenever something goes off the average, the baseline, we have alarms. We have people who start addressing these issues straight away. We have less than 20 minutes. Any questions so far? Anything you're curious about? Yes, Muhammad.
Is this what is called a pipeline? This is a pipeline, or architecture is different?
No, this is not a pipeline. A pipeline is in continuous integration and deployment.
Yes.
Something else. Maybe we can talk about continuous integration and deployment. If no one has questions about this, I can show you how you can deploy applications to this stuff very briefly. Yes, Karim. Yeah, Karim, go ahead. Oh, your mic. Yeah, you can drop it in the chat. I will try to answer. Okay. In the meantime, maybe we can talk about how we build features and how we do continuous deployment and continuous integration. So CI, CD, the holy grail of releasing features at scale. When we talk about teams like Facebook, they definitely deploy changes multiple times a day, not a release once a week. Changes multiple times a day. This is very important, right? CI/CD plays a big role in this, and there are principles for CI/CD. How does it look like? I'm pretty sure you have been using GitHub for a while now, and you have been using some form of a branching strategy. So this is your repository. We start with the first commit, and this is the main branch, right? This is the main line. So you start with the first commit, you add the boilerplate code for Laravel, and then you start building your features. You start adding more and more. These are the dots here are the commits, right? And then when you're working alone, your history will look something like this. You don't really need branches. You might use a couple of branches, but yeah, it doesn't really require a lot of effort. You're working independently from anyone else. There's really not much going on. Let's say I am working with maybe, I don't know, Salma or Karim or whoever from the team, and we are all collaborating on this code base. We cannot really use this, and not everyone can commit to the main line directly. This is not the Wild West. In this case, we start creating something called, feature branches. And a feature branch is basically a branch that you create from the main line directly. And you start committing to that branch. I'm going to call this branch Bassem /F1, which basically means feature 1. And then I start adding my features, new files, new things that are happening. Great. At the same time, maybe some other people are committing to the main line. And at the same time over here, I don't know, Salma or someone else come here and they create a branch from this point, and then they start adding their features. So this one is called Salma F2. Salma is adding more stuff, and I am building my own stuff over here as well. The main line will always continue, right? Think of this as here, the arrow of time. Okay, so what happens when I am ready to merge my changes, when I want to share my changes with everyone else? I don't ask everyone else to come and copy my branch. No, I create a pull request. We're going to call this PR. What happens on the pull request level? This is where things become interesting. In the pull request, we will run in a continuous integration setup unit tests. If you don't have unit tests, forget about continuous integration. It will not work, period. If you don't know what unit tests are, don't even think about continuous integration. Learn unit testing first. Learn how to write good unit tests. Unit tests will allow you to guarantee and verify that the rest of your application did not break because of the changes you introduced right now in this branch. If you don't have unit tests in your environment, at least unit tests, forget about continuous anything. You cannot do it, period. Okay? So unit tests are fundamental. The next step that comes after unit tests is doing some maybe integration tests. If your application needs some other systems, or if you are in a microservice environment where you want to test changes across multiple services and you have integrations, you have databases, you have stuff, integration tests are important. And what I mean by those is not someone coming in and clicking buttons here. No, I'm talking about full automation. You have a lot of tools that you can use. Laravel has a very nice unit testing library. PHP has a nice unit testing library that you can use. There are third-party tools that you can, with which you can build nice integration and unit tests. The more advanced your tests are, the more confidence you can have in your pipeline. And I'm going to describe what a pipeline is right now. So unit tests, integration, and then when you might want to do some builds, and by build I mean generating an artifact, right? When you an artifact could be a tarball, it could be a zip file of all of the files and changes that you have in your current pull request, or the changes you have introduced. Next, once we do the build, we want to maybe deploy to staging. And you might say here, but Bassem, you said we don't use staging environment. That's correct. We don't use them in the traditional sense. But what we will do here is we will spin up a new environment, a complete environment. It could be a combination of an EC2 instance plus a database, right? And on this environment, we will get the build that we have generated in this step, and we will deploy it to the staging. And this staging environment is accessible to me and the team. And it is very specific to the PR over here. It's not like a staging environment, one environment for everyone in the team. No, this is one environment just for me. Okay? And this is where I can come and tell the QA team, for example, the quality assurance team, to come and do their clicking or testing or validation that is visual, manual. It depends on what you're building. This process might not be necessary, but let's just say that it could be one thing, right? So these steps that I've just described over here, these are called a pipeline, right? These are steps, jobs, stages of a PR. Oh, wow, we forgot one very important thing. Code review. If you don't do code reviews, what's the point of anything in life anymore? Let's go back to the wild, wild west and build software like we did in 1991. Even in 1991, there was a code review process. Bottom line, this PR has went through all of these different steps successfully. We have deployed it. Everything is working great. We have checked it visually. Everything looks fine. Now we need to merge this PR with the main branch. We have some automation that automatically merges this with the main branch. Now, what happens when the PR is merged on the main branch? I will tell you what happens. Exactly these steps will happen again. So unit tests will run. But what are they running on? they're running on the changes that come from this PR plus all of the changes that came through the main line, because other people might have introduced stuff that might break the changes I've just introduced, right? So I want to make sure that the unit tests pass, and then I want to run the integration tests, and then I want to run the build one more time, and then I want to generate the artifact. And this time, instead of deploying to a staging environment, I deploy to production. After these steps have passed, then I will deploy to production. And then does it handle conflicts automatically? Great question. I will respond to this. So I will deploy to production if all of these steps pass. No, it does not handle conflicts automatically. Why? Because if there is a conflict, the unit tests will fail, the integrations will fail, and the builds will fail. And if these fail, then we have to basically go back, fix these issues, and deal with it before the merge happens. So the merge will never happen until all of these checks pass. Okay?
So the conflicts will be handled in the unit tests?
No, the conflict will never be handled by the unit test. The unit test is just an indicator that you have conflicts, that you have issues. The unit test will not even run if you have conflicts. So the merge that will not happen here anyway if you have conflicts.
Okay, so we have to manually check for the conflicts.
GitHub will complain. You don't have to manually, you have to visually inspect it for sure, right?
Yes.
You don't just deploy to production and you go home. Okay. But what I'm trying to say is that the tests happen automatically. So you merge, you don't have any conflict because you were able to merge, but still you don't have any confidence that what you merged works with the rest of the stuff, right? Irrespective of conflicts. You might not have a conflict, but still your changes have broken the code. Right? Good question. I'm happy to clarify this. So we deploy this to production. When we deploy this to production, again, we talk about release queues and all of that stuff. Now you will ask me, Bassem, if you have a setup that looks like this, we have, I don't know, here 5, 6, 7, 10 web servers. How do we deploy to production? That's where automation comes into play. The role of the pipeline is to come and say, web server, to do Canary releases, to say web server 1, you get this chunk. Web server 2, you get this new release. But web server 3 and 4 and 5, you stay on the old release. And the load balancer is distributing traffic, right? So the load balancer will be changed to say that, please make sure that 20% of the requests that come to you, they go to web server 1 and 2, because we want to test these changes and make sure that we don't have any problems. And then when these users face problems in production, we are capturing those in the monitoring over here, right? We are capturing those over here, and then the engineer who's releasing to production, they are looking at the dashboards, they are looking at the 500 errors, they are looking at the 200 errors, and if we see spikes, then we say, okay, this stuff, even though all of these things have passed, but still this is not a good release, so we need to roll back. And then you're going to ask me the most important question of the day, which is, Bassem, great, we released the code, but what happens to the database? How do we release changes to the database? How do we deal with a cluster of databases? This topic is the content of another tech talk. Maybe we'll do it after you graduate from SE Factory, or maybe it's something I will cover on my YouTube channel. But yeah, these are really advanced topics. I hope I was able to share with you something relevant and interesting. I think we have walked through the journey of building Facebook from, simple 3-tier architecture to a vertically scaled and horizontally scaled architecture with geographic distribution, load balancers, database replication. And then we went to the extreme end, which is deploying something that, handles well with different regions across the globe, and it does auto-scaling. And it serves a huge number of users. Now here we're talking about millions of users across the globe. And we talked also a little bit about CI/CD, but this is the gist of the continuous integration, continuous deployment topic. And I think I covered the essentials and the basics of what you need to know. We have 6 minutes left. Do you have any questions? Please go ahead, Muhammad.
Yes, I have a small question about the pipeline. You said the pipeline is private to you, to Bassem, right?
Yeah.
But Salma is also committing on the main branch.
Excellent.
So she just to continue the question. Sorry, shouldn't she have the same pipeline?
Yes, but the pipeline is not private to me. So the pipeline is a bunch of jobs. I will get a fork. I will get a copy of these jobs running for me in my pull request. I will be able to see their status. If Salma is introducing changes, she will have her own set of jobs in her own PR. Right? And again, just to clarify over here, these changes over here, they were not introduced directly to the main branch. These came also through a PR process. But I just, for the sake of speed, I just added them right away.
So when you commit and push your code to the pipeline, you run the testing and codes to see if it merges well. After
you don't push it to the pipeline. You just create a pull request, and the pipelines are configured to run on the content of the pull request.
Okay, so when you run a pull request, you don't have to push it again?
Yes, you do. When you're done with all of these things and you deploy to staging and you confirm that everything is fine, you merge the pull request with the main branch.
Yes, through automation.
Yes, through automation, and then the tests will run again.
Okay.
Great questions. Anything from anyone else? 4 minutes left. I know it's dense. We covered a lot of stuff. Do you talk about my journey into software engineering on my YouTube page? Yes, actually, I have an episode called "How Far Can You Go as a Self-Taught Software Engineer?" It went live a couple of weeks ago, but there's a recording on the channel. You can check it out. Awesome. What else? Anyone else has anything they're curious about? This is your time. Yes, Karim.
When you were talking about not to over-engineer before when we're setting up like our app, is it just to avoid like to be cost effective, or does it pose any other problems?
I mean, this takes a small village to maintain. So if you can afford the payroll of a small village, please be my guest. Build something like this for 100 users, right? We're not going to complain. And if you have the money for this infrastructure. But what I'm trying to say, if you have, when you go to a company or a startup, you have limited resources, you have limited assets, you have limited money. You cannot build stuff like this. So you have to gradually build up your environment, depending on the traffic that you get and depending on what you can afford. Yes, I will share the PDF for the notes. Any other questions? I have a question regarding forks on GitHub. Is there a solution to restrict it if our repository is public? I think you can disable forks, if I'm not mistaken. No? You can disable forking on your project. You can go to the settings of your repo and disable forks. Why? What are you worried about? You're worried about people forking your project?
Someone forked my project. So I did it private, but it's still there. I don't know. Just
contribute to open source. Don't worry about your project unless you have like $1 million idea. It's okay.
Okay, thank you.
No problem. But I think you can disable forks in the settings of your repository. Any other questions before we wrap up?
Yes, just a small question.
Go ahead.
A small question. If we want to upgrade the architecture of the software, adding firewalls, DNS, and these stuff, everything happens while we're running the website, so it doesn't affect the...
Well, of course, every change you introduce will definitely affect something. So you have to do your analysis. There's no magic in here, right?
But you don't have to shut down, I mean.
Sometimes you do. Sometimes you do. Nothing can go. You cannot have zero downtime deployments right away from the get-go. Sometimes you have to shut stuff down.
Okay.
Can you transform vertical to horizontal? Yes, Kalim. They are not mutually exclusive. All right. Thank you very much, everyone. This has been amazing. I would love to talk to you more, but we ran out of time. I wish you the best of luck on your journey. I hope we meet again. And I hope I was able to share with you something useful today. Good luck and take care.
Bassem, thank you for this great talk. Thank you, Bassem.
No problem. My pleasure. Take care, everyone.